Hi again, everybody. Welcome back. We've been talking in this chapter about how torque is basically a force applied in a turning motion. And what I think what you'll find is that as we continue this chapter, the forces chapter that we talked about several chapters ago, we're going to find a lot of correlations to that. This is simply applied in a turning direction. Let me back up a second right here. We talked about how if a force is applied at some radius, all right, it causes a torque around that central point. And so if the force is a little off axis, or at least non-perpendicular to the radius, we found what we call the moment arm, or that is the kind of the hypothetical right angle radius that force will be applied to. But it still is a force, and it's a turning force. And so as we start talking about torque, which is really a force applied at a radius, we need to start establishing you might say, an axis, or a point of origin, a positive and negative, because if force can be positive and negative, so can torque be. All right. Well, if a force, and this right here is just kind of some conventions and special conditions right here. If a force is radial, that means, let's say we have a I don't know, something that you want to turn, say a doorknob, okay? You want to turn a doorknob and you want to open the door like that, okay? You want there to be some sort of torque right there. What happens if you apply a force radially to it? If you apply a force right to the center? Nothing, right? You want to apply it at right angles to the radius. Or if you apply a force outwardly like that. If that's your force right there, if the force is radially directed, then you've got zero torque. You want the force that you apply to be at some angle to the radius. And if that's the case, then you're going to get some torque. All right. When you've got a tangential force, kind of like I just drew, that green one right there, the force is tangent. Here's our force and here's our radius. If they're at right angles to each other, or if they're tangent, the force is tangent to the turning circle, then your torque is simply radius times force. Now that's sort of an abbreviated version of what we talked about in the last segment. We say torque is radius, vector radius times force times the sine of that angle between them, right? Well, if that angle is 90 degrees, then that sine of 90 is 1. All right, so that maximizes your torque. If you want to turn this doorknob, but you apply a force tangentially, yeah, of course, then it's going to turn, and you're going to maximize your torque. And direction-wise, all right, well, direction, just like we talked about in rotational kinematics, if something is rotating counterclockwise, we'd say it has a positive acceleration, or a positive velocity, or in this case, it's got a positive torque. It's greater than 0. If it's if it's clockwise, so if it's going this direction right here, we say it has a negative torque, or it's less than 0. All right, so that's some of our cases right here. Basically, if you want to turn something, don't apply a force right to the center because it's not going to turn. If you want to maximize your turning force, apply a force at a tangent or at right angles to the radius of your axis of rotation. Counterclockwise is positive, clockwise is negative. All right, so let's do an example. So here we have a ship helm. A helm is that thing that you see, well, right there at the bottom, right there. It's what you turn to turn the ship. And apparently we have two helmsmen who are in disagreement about which way a ship should turn. So they're they're applying forces in opposing directions. So they're applying opposing torques around this helm right here. All right. Well, let's take this. And first of all, I'm going to have to shrink it down because I know I'm going to need some more space here. Okay, like that. Let's write down our notes first of all, okay? What color am I in? I'll write this in blue, all right? Our radius, first of all, is 0.74 meters. So that's a pretty big, it's 3/4 of a meter right here, so it's about about 1.5 meters across, so it's a big wheel. All right, radius is of 7.4 meters. So our force from helmsman 1 is 72 newtons. So F1 equals 72 newtons, and you'll notice that it is generally the counterclockwise, it's being applied in the counterclockwise direction. Force 2 The other helmsman is 58 newtons. Okay, and that's going to be applying a torque in the clockwise direction. So they're obviously opposing each other, and force 2 is going to be creating a negative torque. We want to find A, the torque caused by F1 and the torque caused by F2, all right? And so ultimately we want to find what direction, basically who wins, what direction does the wheel actually turn, okay? What is going to be, you might say, the net force applied at that radius, and ultimately what is the net torque, all right? So A right here, the torque from 1 is going to be the radius, okay, which we know, times force 1 times, oops, I shouldn't have written my equal sign quite just yet, times the sine of the angle between them, right? So our radius, that's going to be easy. That is 0.74 meters. The force is 72 newtons, and the sine of the angle between them. Okay, this is interesting. So here's our radius, and then the angle we were given right here is 50 degrees. All right. If we take this radius and extend it out, like so, like that, is that the angle we want, or is it the complementary angle? This right here is actually the angle that we want, right? We don't need to worry about that 40 degrees over here because, remember, vectors can be transferred from one point to another. And so if this is our radius, or you might say, I'll draw that in light blue right here, kind of match it. So that's your radius. We could sort of transfer it up here and say, all right, well, our radius vector is right there. The angle between them, between the radius vector and the force, is in fact that 50 degrees. So we're going to have to account for that 50 degrees. So radius times force times the sine of that 50 degrees right there. All right. Now it is degrees. If your calculator is in radian mode from last chapter, you might need to switch back and forth. We talked about radians in terms of things rotating through, a certain number of revolutions. But this angle right here, we're actually still going to measure in degrees. All right. So if you want to convert that to radians and then use radian mode, that's fine. But with this angle, make sure you're using degrees. All right. Well, what does that come out to be? 0.74 times 72 times the sine of 50. I get that is 69.6, which is actually going to round up to 70 newtons. Now, what direction is that going to be going in? That's going to be, force 1 is going to be creating a force or creating a torque that moves counterclockwise, so that is positive, right? So torque 1 is at 70 newtons right there. Well, B, we're asked to find torque 2. So torque 2 is the radius times force 2 times the sine of the angle between them. All right, now look at these two red arrows right here. So this guy is applying a force kind of upwards and away from the center of rotation. All right, it's not at right angles. It's at 50 degrees from the radius. This guy, force 2, is applying a torque or a force, directly at right angles to the radius. All right, we're told that's a 90-degree angle right there. And so who is actually applying a more effective force? It's going to be this guy, right? Oops, I kind of drew over that. It's going to be helmsman number 2, right? If you want to turn something, you apply a force at right angles to the turning radius, and that's exactly what he's doing right there. So that sine is going to be 90 degrees. So that's going to be the radius, which is 0.74, times force 2, which is 58 newtons. So he's applying less of a force, but with a sine of 90 degrees, let's see what that comes out to be right there. So I get 0.74 times 58 times, oh, I made a mistake here, 58 times the sine of 90 degrees now. What do we get? 42.9 or 40, I guess it'd be like 43 newtons. Oh, and you know what? I realized I messed something up. Let's go back to, I set this up right, but I didn't key in my calculator right for the previous problem, the prior problem right there. That was my mistake. I still make mistakes. Let's go back to part A a second. First of all, 70 newtons, that's not even the right units, is it? I just keyed in 70. That's what happens when you do your first example. You're still a little bit rusty. Let's redo this, and let's redo part B. Actually, you can leave it all still set up. I just need to do my calculations again, all right? My apologies. Part A, I had to accidentally put a dividing sign in here instead of a multiplication sign. So 0.74, I'm going to do this out loud now, times 72 newtons. So by the way, that 0.74 is meters, right? So the answer should be Newton meters. 0.74 times 72 times the sine of 50 degrees. That is not 70. That comes out to 40.8, all right? So that should be 40, this guy is 41 Newton meters. So that's torque 1 right there. That whole thing, that was all messed up. That's my mistake. So now, all right, so this guy's force is greater, but it's at this angle right here. This guy's force 2, is less. He's only applying 58 newtons. Now it's going to make our answer to part 2 make a little bit more sense. So torque 2, again, I accidentally had a dividing sign instead of a minus sign in there. 0.74 times 58 newtons times the sine of 90 degrees. Of course, we know that's 1. That's going to be 40, like I said before, 42.9, or actually 43 Newton meters right there. Now, this guy is applying it in the clockwise direction, which is going to make this negative, right? That's going to be a negative 43 Newton meters. So, who's going to win? Who's going to win? Well, helmsman 2, right? He's applying a greater torque. So, this is actually, I'm going to just call this part C, even though it's not labeled like that. We're going to write this as net torque, right? That's going to be torque 1 plus torque 2 plus any other torque, right? Just like net force is the sum of all the forces, net torque is the sum of all the torques. So that's going to be 41 Newton meters plus negative 43 Newton meters. I think we can do that in our head. That's a net torque or total torque of 2 or negative 2 Newton meters. And to answer the question, in what direction does a wheel turn? It turns clockwise, right? Because that's the negative direction right there. So I apologize for this part right here. I accidentally put a divided sign in instead of a time sign. But it goes to show that you can actually apply less of a force, but as long as it's at more of a right angle to your axis of rotation, you're going to actually create a greater torque. All right? So I'm going to wrap it up for this segment right here. Thank you for following along. Ask me if you have any questions, of course, and I'll see you on the next one.